Hi guys, my name is Ramprasad. I am saying about the operating systems lab. Experiment number 5, classic problems on synchronization using semaphore. Write a program to simulate the concept of radar. Write a problem using C++ or Python. Write a program to simulate producer consumer problem using semaphores using C++ or Python. Write a program to simulate the concept of dying philosopher's problem using C++ or Python. And semaphore synchronization tool and all provides and all tool that provides more sophisticated ways that mutex for a process to synchronize their activity. Semaphore as integer variable can only exist via two visible atomic operations, wait and sign. Or and let's see the first one. Producer consumer problem. Producer consumer problem is a common paradigm for operating a process. A producer process provides for information that is consumed by a consumer process. One solution to the producer consumer problem uses shared memory to allow producer and consumer process to run concurrently. There must be available a buffer if items can be filled by the producer and filled by the consumer. The buffer will reside in a region of memory that is shared by the producer and consumer process. A producer can produce one item while the consumer is consuming another item. The producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. And buffers can hold one item. Semaphore mutex initializes to the value semaphore fully initialized to the value 0, semaphore empty initialized to the value, and we need to get the output. The sample output is like this, and we can see the program. Global mutex empty full def wait find. If find is equals to empty, global empty is equals to empty minus is equals to 1. Else find is equals to mutex. Global mutex minus is equals to 1. If else find is equals to full, global full is equals to full minus is equals to 1. Define signal. Find if find is equals to empty, global empty plus is equals to 1. Else if find is equals to mutex, global mutex plus is equals to 1. Find else if find is equals to full, global full plus is equals to 1. And n is equals to n is equals into input and buffer size. Buffer is equals to mutex is equals to 1, empty is equals to n, full is equals to 0, while 1 print, 1 produce, 2 consumer, 3 t exit. Choice is equals to into input, enter your choice. If choice is equals to 1, if mutex is equals to 1, empty exclamatory is equals to 0, print, enter the value, wait mutex, buffer dot append input, signal mutex, signal full, else print buffer is full, else if choice is equals to true, and if full less greater than 0 and mutex is equals to 1, wait full mutex, print the consumer value is string string buffer dot pop len buffer minus 1, and signal mutex signal empty, else if print buffer is empty, else if choice is equals to 3, break, else print is invalid input. Let's run the program, and you can give the buffer size as 3 and enter your choice. So buffer is empty and 1, and enter the value 100, enter your choice 2, and consumed value is produce 100, 1 produce, 2 consume, 3 exit, and exit. See the second one, reader's writer problem. A date setting is shared among a number of current processor. Reader only read the data set. They do not perform any updates. Writers can both read and write. Problem. Allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. Several variations of how readers and writers are considered all involve some form of priorities. Shared data set, semaphore write initialized to 1, semaphore mutex initialized to 1, integer read count initialized to 0, and we need to get the output as sample output reader 1 or, and we need to get this output, and let's go to the program. From form random input shuffle choice global mutex empty full index index count writer define wait find if a find is equals to empty global empty minus is equals to 1 else if find is equals to mutex global mutex is minus is equals to 1 else if find is equals to full global full is minus is equals to 1 else if find is equals to right global right is minus 1 minus is equals to 1. So you find signal find is equals to empty global empty plus is equals to, and empty plus is equals to 1 else if find is equals to mutex global mutex plus is equals to 1 else if find is equals to full global full plus is equals to 1. Define reader count is equals to 0 wait mutex reader count plus is equals to 1 if reader count is equals to 1 wait writer signal mutex global count index print reader plus string index plus read cut as string count index plus is equals to 1 if read count is equals to 0 signal write signal mutex define writer wait writer global count index count star is equals to 2 print writer plus string index modified cnt2 plus stringer count index plus is equals to 1 signal writer mutex is equals to write is equals to count is equals to write index is equals to index is equals to 1 read count is equals to 0 fns reader writers for I in range 15 choice fns, and let's run the program, and we got the output. We got the same output. Reader 1 read cnt as 1, reader 2 read cnt as 1, writer 1 modified cnt to 2, reader 3 read cnt as 2, writer 2 modified cnt to 4, writer 3 modified cnt to 8, writer 4 modified cnt to 16, reader cnt as 16, reader 5 cnt read cnt as 16, writer 5 modified cnt to 32, reader 6 readers CNT as 32, and Radar 7 CNT read CNT as 32, Radar 6 modified CNT to 64, Writer 7 modified CNT to 128, Writer 8 modified CNT to 256. And let's see the third one, dining philosopher's problem. The dining philosopher problem is considered a classic simplified problem because it has an example of a large class of concurrency control problem. It is a simple representation of the need to allocate several resources and several processes in a deadlock-free and starvation-free manner. Consider 5 philosophers who spend their lives thinking and eating. The philosopher chair as a circular table surrounded by 5 chairs, each belongs to one. Philosopher is in the center of the table is a bowl of rice, and the table is laid with 5 single chop chopsticks. When a philosopher thinks, she does not interact with her colleagues. From time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks and that are closest to her. Chopsticks that are between her and her left and right neighbors. A philosopher may pick up only one chopstick at a time. Obviously, she cannot she cannot pick a chopstick that is already in the hand of their neighbor. When a hungry philosopher has both her chopsticks at the same time, she eats without releasing her chopsticks. When she is finished eating, she puts down both of her chopsticks and starts thinking again. The dining philosopher's problem may lead to a deadlock situation, and hence some rules have to frame to avoid occurrence of deadlock. And we can see the output here. And let's go to the program. Let's run the program. From a random input choice, global A define weight pro process number. Global A process number minus is equals to 1 define signal process number. Global A process number plus is equals to 1. A is equals to 1 comma 1 comma 1 comma 1 comma 1, while 1 y is equals to 0 process numbers is equals to 0 comma 1 comma 2 comma 3 comma 4. Copy 1 is equals to process number, copy 2 is equals to process number, and p is equals to input 1 can eat at a time, 2 can eat at a time, 3 exit. Print allow if p is equals to 1, print allow one philosopher to eat at a time while I less than 5. Random proc is equals to choice process, random process is equals to choice process number, weight random process plus 1% 5. Print p plus string random process plus is granted to it. Print p plus string random process the is divided by len. Copy 1 plus is waiting. Print p string plus string random process plus len. Copy 1 minus 1 is divided by len. Copy 1 plus is waiting. Signal random process. Signal random process plus 1% 5. And process numbers removed. Random process. I plus is equals to 1 if len process is equals to numbers is equals to 0. Break. Else if process p is equals to 2, allow two philosophers to eat at the same time. C is equals to 0, J is equals to 0, while J less than 5. Random process is equals to choice copy 1 with weight random process plus 1% 5. P print p plus string random process plus and plus p plus string random process plus 2% 5 are granted to it. Print p plus string random process plus 3% len copy 2 plus is waiting. Print p plus string random process plus 4% len copy 2 plus is waiting. Print p plus string random process plus 1% len copy 2 plus is waiting. And single random process signal random process plus 1% 5. Copy 1 remove random process. J plus is equals to 1 if len copy is equals to 0 break. Else if p is equals to 3 break. Let's run the program. And option 1 can eat at a time, 2 can eat at a time, and I am giving the option as 1. The output as came. Allow one philosopher to eat at a time. P2 is granted to eat. P3 is waiting. P1 is waiting. P3 is granted to eat. P4 is waiting. P2 is waiting. P4 is granted to eat. P0 is waiting. P3 is waiting. P0 is granted to eat. P1 is waiting. P4 is waiting. P1 is granted to eat. P2 is waiting. P0 is waiting. And 2. I hear the number as 2. Option 2 is allow the two philosophers to eat at the same time. P4 and P1 are granted to eat. P2 is waiting. P3 is waiting. P0 is waiting. P3 and P0 are granted to eat. P1 is waiting. P2 is waiting. P4 is waiting. P0 and P2 are granted to eat. P3 is waiting. P4 is waiting. P1 is waiting. P1 and P3 are granted to eat. P4 is waiting. P0 is waiting. P2 is waiting. P2 and P4 are granted to eat. P0 is waiting. P1 is waiting. P3 is waiting. 1 can eat at a time. 2 can eat at a time. We can also find. Third one is exit. I have given the third one. And thank you guys by watching my video.